Hey guys, welcome back to the channel. I hope you're all doing well. I don't know about you, but the weather has been consistently bad out here in Northern California for the last couple of months, and I have not been able to do any kind of imaging. So I thought it was an appropriate time to talk about equipment. And today I have something really good to show you. We are going to take a look at this revolutionary new electronic focuser. This is an open source DIY project, but it is also available for purchase for a limited time via crowdfunding. So let's get started. This electronic focuser can be used in a variety of setups, and I'll cover those in more detail towards the end of the video. But first, let me explain how it came to be. If you are a long-time subscriber to my channel, you may remember that when I got started in astrophotography, I was using a guide scope. At the time, I had some differential flexure somewhere in my system, which was giving me oblong stars, even though PHD2 was reporting excellent guiding numbers. Instead of painstakingly going through the process of identifying the source of that flexure, I decided to switch to an off-axis guider, or OAG. And sure enough, that immediately resolved my issue. Now my stars are perfectly round, which is great, and my guiding numbers are even better than before. However, the OAG brought a number of new challenges. First, when using an OAG, the field of view is very small, which sometimes makes it difficult for the guiding software to detect guide stars, especially during galaxy season. Second, the OAG may require some amount of refocusing when switching filters. Let's take a look at why that might be. In this diagram, you can see what an imaging train with an OAG looks like. The OAG pickoff prism is placed in front of the filter. You never place the OAG behind the filter for two reasons. First, if you were to place the OAG behind the filter, your guide exposures might need to be very long, especially if you use a narrowband filter. As a result of those longer exposures, your guiding accuracy would be lower. Second, your filter being slightly further away from the sensor may cause some additional vignetting. So remember to always place the OAG in front of the filter as shown in this diagram. Note that both the guide camera and the imaging camera are in perfect focus at this time. Now let's switch to a different filter. This causes the focal plane to move ever so slightly. That is because filters are not always parfocal, especially if they're not all from the same set. Also, refractors, even apochromatic triplets, will focus various wavelengths at different distances. Modern image acquisition software, like Nina, can automatically apply a filter offset upon switching filters to compensate for this shift in focus. If you want to learn more about filter offsets, I have a video that explains all of it in great detail, and I recommend you check it out. Once the filter offset has been applied, the imaging sensor is able to once again produce a sharp image. However, the guide camera is no longer in focus. In some setups, this effect is sufficiently subtle that it can be ignored. But sometimes it can be a real problem, and to prove it, let me show you what my guide camera sees when I switch from my Astronomik L3 filter to my Antlia red filter. No matter how good PHD2's star detection algorithm is, it will detect fewer stars, and the centroid of the detected stars will not be as precise as if you had a sharp image. Occasionally, and especially during galaxy season, the guiding software may not be able to detect any star, and guiding will fail. Usually that happens in the middle of the night when you're sound asleep. The solution is to get up in your pajamas in the middle of the night to adjust the focus of your OAG. But that gets old real quick, so I eventually came up with a better solution, and it comes in the form of this little device, coupled with some software I developed for it. This electronic focuser, which has an M42 female thread, can attach to an OAG, like the one from ZWO, and upon switching filters, the software can automatically instruct this device to precisely compensate for the filter offset so that your guide camera is always in perfect focus. Let's take a look at the result. As you can see, this device works very well as an OAG focuser, and that is what it was originally designed for. But it can also be used to focus the entire imaging train on any lightweight setup. For example, it works great on a small telescope like the Skywatcher EvoGuide 50 when riding on a star tracker. Some people have used this device to remotely focus their guide scope because large temperature changes between summer and winter can have a significant impact, and if you have a fully remote setup, it's nice to be able to run an autofocus routine remotely on your guide scope. Others have used this device on their high-resolution spectrograph to remotely and even automatically refocus the imaging camera when changing the wavelength they're studying. It is a very versatile focuser. Please note that the software is currently only available for Windows, so it will not work for Mac OS X or Linux users, and it certainly will not work on an ASI Air. However, I am planning to create an Indy driver for this device later this year, and if you want to beat me to it, I will gladly accept your contribution in the form of a pull request. The first version of this project, which I created a couple of years ago, had a few minor design issues. First, it required two cables, a 12-volt DC cable and a USB Type-C cable. Also, it was a little bulky and it had a bit more backlash than I would have liked, even though the software was able to compensate for that. This new version requires only one USB Type-C cable. It is a bit more compact than the first version, and it has almost no backlash thanks to the herringbone gear and pinion. Also, the software can now be installed using an installer, instead of requiring semi-obscure command line instructions that a lot of you seem to have struggled with in the past. Of course, this new version is still open source, and the project is still hosted at the same GitHub repository, and I'll put a link to it in the description below. So if you want to build this project yourself, you can still do so. However, over the last 2 years, a lot of you have reached out to me to ask if I would be willing to build this device. Well, the big news is that it is finally possible to purchase this product. I am making it available for a limited time via a crowdfunding campaign on Indiegogo. I decided to use a crowdfunding platform because I am planning to manufacture a batch of focusers. This way I can make it available to you at a really low price. I will put a link to the crowdfunding campaign right here and in the description of this video. Note that I will only ship to the US because I don't want to deal with the complexity of international shipping, which involves customs duties and VAT. And for such a small crowdfunding campaign, dealing with an international fulfillment company does not make sense. Up until now, if you wanted to remotely control a helical focuser, you had to buy the helical focuser itself, a ZWO EAF, and a bracket like the one available from Agena Astro and sold by Buckeye Stargazer. The result is quite bulky and heavy, and it costs over $300 US. Thanks to my Indiegogo crowdfunding campaign, I am making this device available for $179 US, including shipping. Also, this device is quite compact and very lightweight. To ensure quality, each unit will be individually tested prior to shipping, and I will even measure the backlash for you. The crowdfunding campaign starts right now, and pledges will be accepted for the next 30 days. So if this is something that you are interested in, don't wait, and please know that the money that you pledge will help support this channel. Even if you are not interested in this product, you can still support this channel at no cost to you. Your support and encouragement is really what keeps this channel going. You may have noticed that I try to cover unique topics instead of doing yet another review of the ZW C-Star, for example. Like, how many of those reviews do you really need to watch? Anyway, these unique topics require a significant amount of research, which is why I post a new video only once a month, which is not enough for a YouTube channel to really take off. I do these videos because I feel like I can contribute something good to this wonderful astronomy community. But it has a cost. So, if you would like to support this channel, you can simply comment, like, and subscribe. You can also tell your friends about it. You can click on the affiliate links that I included in the description below if you want to buy anything from my favorite Astro retail store, which is Agena Astro, or anything from Amazon. And if you feel extra generous, you can also send me a tip by clicking on the thanks button located right underneath this video. Or you can click on the Donate with PayPal button in the project's GitHub repository. Every little bit counts, and I am truly grateful for your continued support. All right, I'll be back in a few weeks, so until next time, thank you for watching, and clear skies.